Welcome. My name is Katarina Vukušić. I am from the University of Zagreb, and I am the communication coordinator for the European Processor Initiative. The panelists are all here, as you can see. I welcome them all and thank them for their time. And of course, I thank you for your time for coming to our tutorial. I will now just briefly share my screen to let you know about the agenda that we have today. So as you can see, we will be starting with a general overview and introduction to tutorial topics that will be taken by our colleague from CEA. And later on, we will have other presentations such as hardware security module in the EPI general purpose processor, update of the PCIe boards, simulation framework for the EPI processor, and the power controller. We will have 2 breaks because even though this is a relatively short tutorial, we know that we need some break time from the screen time as well. And at the end, all of our panelists will reconvene at 6:10 to answer more of your questions. Since we had a really big attendance listed at the beginning, which we're happy about, these tutorials and webinars are configured in a way that require the host, which will be me, to allow you to talk. And since there's a lot of you here, we would kindly ask you to write your questions during the presentation in the chat, which I will monitor. And at the end, of course, at the end of each of these presentations, our presenters and experts will take a look at the questions in the chat and answer all of your questions. If we run out of time for answering all the questions, of course, you will always be welcome to contact us, email us, or reach out via social media to us for any kind of other explanation necessary. I hope that's okay. And I will now stop sharing and invite my colleague Denis to start his introduction.
Okay, so first of all, I will share my screen and put it in the presentation mode. Normally, everything should be fine. So, Katarina, is it okay like this? You can see my screen with a pointer?
No, not yet. Are you sharing your presentation?
Okay. Yes. Normally.
It works now.
Yeah, now we can see it.
Okay, thank you.
Now we can see it. Okay, thank you.
With a pointer. Okay, just a few minutes for having everything okay. So my name is Denis Dutoit. I will start this tutorial with some introduction of EPI project. This is the second time we have this tutorial at HiPEAC. We had also once this tutorial at the very beginning of the project in 1.5 years ago. The goal of this tutorial is to provide you with the most up-to-date information on European Processor Initiative project and its related activities. Okay, so let's start with an overview, and then I will introduce a little bit the tutorial topics. So for the EPI overview, each time we have this tutorial, I present these slides, which is the state of the first or more performing supercomputer in the world. This list has been updated last November. So what can we learn from this list? First of all, we are very close to the exascale level of performance. And what we can learn as well is that in terms of users, as well as in terms of chips, design and manufacturing of the processors, nothing is coming from Europe. The major information from this last list is that the Japan is back with the first supercomputer, the more performing one, with their microprocessor, processor Fujitsu A764FX. But on the European side, nobody is present in this list. So the question is how to bring back Europe into the processor race. And this is actually answered by the Euro-HPC joint undertaking, which is a joint initiative between the European Union and European countries, and also private partners to develop a world-class supercomputing ecosystem in Europe. So the Euro-HPC is a legal and funding entity. It has been created in 2018 and is located in Luxembourg. The joint undertaking allowed the EU and Euro-HPC participating countries to coordinate their efforts with the objective of deploying in Europe world-class exascale supercomputers and also developing supercomputing technologies. And as of October 2020, there was 32 participating countries in this Euro-HPC joint undertaking. Currently, the joint undertaking Euro-HPC is supporting the following activities. First, to develop world-class supercomputing infrastructure by procuring and deploying by 2021 3 pre-exascale supercomputers and 5 petascale supercomputers. So these new machines will be located across the European Union and will be available to Europe's private and public users, scientific and industrial users everywhere in Europe. Another activities is to make supercomputing resources in many application areas available to large number of public and private users, including SMEs. And there is also an activity around technology by supporting research and innovation activities. So in this context, the European Processor Initiative, or EPI, proposed and comes as a result of European strategic plan to support the next generation of computing and data infrastructure. This is driven by a wide range of application needs around societal challenges, as the one you can see here. Sorry, I will not go all over that one, but this is one of this is the first drivers of the EPI processor to be able to provide computing processors able to handle this all these processing applications. Another driver of so even if the main activity of the EPI is to develop a processor for HPC sector, as we have seen just before, another EPI activities and drivers will focus on the automotive sectors. So within the EPI, the automotive stream activities are driving innovation in the automotive industry, including the introduction of autonomous driving and the connected car infrastructure. The really specific challenge in the automotive sector is the integration of high-performance processors that have to be compliant with the environmental requirements in that real-time domain. So that would offer implementation of vehicle perception tasks in a real-time operation mode, increase computing performance, and also compute resources with the same characteristics as their, let's say, big brother in exascale class supercomputers. Now, the EPI, so it's a project which is currently implemented under the first stage of the Framework Partnership Agreement, FPA. So first stage means the first SGA. We call it SGA 1. The European Processor Initiative is gathering 27 partners from 10 European countries. And the leading organization is Atos from France. And you can see here the complete list of partners with industrials, SMEs, larger enterprise, academics, and so lots of partners involved. Our project objectives is to deliver a high-performance, low-power processor, implementing vector instructions, and also to deliver specific accelerators with high bandwidth memory access. The EPI processor will also meet high security and safety requirements. So this will be achieved through intensive use of simulation. We have a presentation about that, and development also of the complete software stack. The chip will be taken out in the most advanced semiconductor process node. So we will have short-term objective. First of all, to supply the UE microprocessor to empower exascale machine in Europe, and longer-term objective for sovereignty and to ensure, let's say, sovereignty of Europe's regarding low-power processors from IP to products, and also obviously access to high-performance machines. As let's say summary, the project will first define the roadmap of processors. Then we are, let's say, developing the first generation of technologies through a co-design approach. IPs for general purpose HPC processors, for accelerators, for trust chips, and we develop as well software stack and boards. During the project, we are at the we enter into the we have just entered into the third and last years of the 3 years project. At the end of the project, end of November, we will tape out the first generation of general purpose processing chip. At the end of the project, we will have validated the accelerator technologies through a test chip made of RISC-V based accelerators. And we will also validate all these technologies in automotive context using a demonstration platform we are currently developing. So these are very shortly described the EPI objectives. I will just start the, let's say, technical presentation with a few words about the EPI common platform. So these slides has been prepared by Cyper, and I will present them. So within EPI, I'm working I'm leading the global architecture work package. And within this work package, we are defining what is the common platform. First of all, common platform is about heterogeneous architecture. And why do we need today to define chips or system of chips able to, let's say, to integrate what we call heterogeneous integration? We can see here in this slide that processor architectures has always followed the semiconductor technology evolution to provide more and more computing performances. So the story started with monocore architectures. At that time, it was possible to improve performances through bigger cores and higher operating frequency. But around 2005, there was what we call the frequency wall. It was no longer possible to increase the frequency. Then the architects moved to many core architecture with more parallelism in order to improve the processor computing performance, thanks, as I said, to higher parallelism. But then came the power wall. So the way the architects overcame this power wall was to move from generic processors or generic multi-core processors to power optimized accelerators. And this power optimization has been made and is currently made through specialization of some part of the application with hardware accelerators. That's why, and obviously for legacy, we still keep generic processing. So that's why we call this kind of architecture heterogeneous many-core architectures, with one part of generic general purpose processing and one part of accelerators. And this is exactly what we are developing within EPI. and what is the common platform about, just to be able to, let's say, in a seamless way, to integrate generic processing with accelerators. Okay, so within the EPI project, we are developing heterogeneous architectures, and we have to integrate them in a clever and a seamless way. And that's why we propose this common platform concept to enable seamless integration of accelerators. This is our, let's say, EPI answer to heterogeneous integration. So this common platform capable design we are developing with the within EPI will allow integration of customized function in chip. Here, this is a chip boundary. In package, here, this is the package boundary. On board, and also over the network link at this level. The EPI accelerators will work are working in I/O coherent mode and share the same memory view at the generic processing. We can handle single or dual chiplet package for power efficient sizing. The goal, obviously, is to increase the byte per flop ratio KPI. The I/O we have defined in the common platform compatible design are HBM2E and DDR5 for memories, and PCI Express Gen 5 for network connection. Within the chip, we have a coherent network chip with system level cache in order to keep data as much as possible local. And finally, we are developing a die-to-die interface open to EPI and beyond. So let's go a little bit into some details of this integration. Let's start just before going on with some details. Common platform is not only an our design able of heterogeneous integration, is not only hardware or integration or package integration. This is also dealing with software. We need to define the complete and to develop the complete software stack, as well as methodology. The goal for the methodology is to put together architects with application experts in order to co-design based on model and simulation tools. We will have a talk about that later on. I was talking about heterogeneity in EPI, or heterogeneity in terms of computing units as the following. The generic processing is made with ARM cores with a scalable vector extension. Then we have several accelerators, MPPA, multipurpose processing array, for, let's say, more real-time processing possibilities. We are developing as well RISC-V based accelerators and also embedded FPGA. So now the goal is to put together through these common platform concepts these different computing units. Let's have some, let's say, example with on-chip heterogeneous integration. The way to integrate accelerators could be to integrate an IP. So accelerators, let's say, it could be an IP, and we can integrate it internally to the chip, to the common platform design. For that, within our chip, the generic processing chip, we've developed. We have the 2D mesh network on chip, to which we can connect our computing units. Once again, the common software environment between heterogeneous computing tiles is harmonizing all their integration, thanks with the external world, memories, but also the PCI Express connection. And this is the view of our software stack. So this is for on-chip heterogeneous integration into our generic processing chip. Then another way to integrate accelerators is off-chip heterogeneous integration with several levels of integration, depending on the distance between the chip itself with the memories and the accelerators. We talked about chiplet when we have another die with a certain function connected to the main host through an inter-chiplet or die-to-die communication, integrating on the same package. We are talking about chiplet within the same package. This is after the internal integration. This is, let's say, the shortest possible distance of accelerator integration within such kind of environments. Then we can define a socket-based heterogeneous integration through, for example, C6 links. With this connection, we are able to use and to put together with the common platform design or generic chip commercial FPGA chips or C6-enabled companion chips. And then there is also a possibility to have accelerators that are IO coherent with the main chip, with the host through PCIe Express links at network level. So obviously, the shortest the accelerator is connected, the less power consumptions you have. So it's in terms of power consumptions, chiplet is much better than a network. As well as the latency, the shortest the distance is, the shortest is the latency between the accelerator and the common platform design or the host. This is also the, okay, once again, we need software to put that and to harmonize all that together. Okay, so this is a very short introduction of what we are developing in terms of architecture and heterogeneous integration. And now I would like to just to figure out this common platform implementation with a roadmap of EPI. This is the overall roadmap with a short-term objective based on the utilization of ARM cores. This is ARM-those cores, and the longer or mid-term objective with RISC-V based on RISC-V accelerators. All these heterogeneous computing units are put together thanks to the common platform with a first instantiation made and developed with from Cypher. First instantiation is 7 nanometer, which is called REA, with availability in 2022. This is the time frame of our first phase of the project. And for this first phase of our project, we are developing and we are targeting processors to be able to sustain petascale and pre-exascale level of performance at the machine, at the supercomputer level. Then following this first generation of processors, the second generation will be called Chronos with still ARM cores and with a general availability after 2023. And this is the time frame for the second phase of the project. So first generation in 2022, second generation after 2023. So this is a really and instantiation in 7 nanometer and for acceleration, which is a longer term objective, development of test chip in 22 nanometer and validation of this test chip, obviously. So as a conclusion, okay, we've seen that we really need of an efficient HPC to provide competitiveness for industry and society. But the expertise for developing such kinds of the high-end processors is no longer present in Europe. So that's why with EPI we have to recover, let's say, this expertise in developing a high-end processor, in designing, in architecturing, in co-designing these processors in order to be able to provide the processors for Europe and for exascale level of HPC systems. So just during this said by Katarina just before, at the beginning of the tutorial, within this tutorial, we will have several speakers. Sergio from University of Pisa. He will talk about the hardware security modules in the EPI general purpose processor. So the general purpose processor is the one implementing the common platform, the one you've seen in the package just before, connected to the memory. After a first break, Fabrizio from E4 will update you on the PCIe boards as development testbed for EPI, because EPI is not only a processor development, but also a board design in order to enable the validation of the processors. I talked about methodology and simulation. So Lilia and Tanguy from CA will describe you the simulation environment and framework of the EPI processor with SESAM and VPSim. And after a second break, Andrea will talk about the power controller of HPC, of the power management we have embedded in our and the simulation on our processors. Obviously, we need to have efficient computing, and power management is really an important topic to be able to sustain power efficient computing. We will have time, if needed, for another Q&A discussion at the end of the.
Thank you, Denis. We have 8 questions already. So okay. I don't know if you see the questions in the question and answer section. There are 6 questions there, and yes, there are 2 more in the chat.
I need to find again my
yes,
my window.
Thank you all for asking questions. This is why I defer them to Denis.
Okay, so this is in the Q&A.
In the Q&A section, yes, you have 6 questions, and there are 2 more in the chat room.
Okay, so the first question is I really like the initiative, thank you. But do you think that the economics will work, and when, in UE favor? And is this initiative only for HPC? So yeah, this initiative is not only for HPC. As I said, we will derive our processors for automotive. That's why the economics will work. This is because we will also develop processors for automotive segments. That's why this economics will work. This is my feeling, my opinion. The other question is, the second question is, how is this initiative different from another one? I have to just.
I think this is the one that was recently signed by several ministers of European Union countries, the one that also calls for next-gen processors.
I would say, okay, I don't know if I have the right guy to answer, but I would say that we are complementary. We really need advanced technology node for our processors. So for us, it's really important to have in parallel this initiative, to be able to have also in Europe, let's say, fabrication of chip, because we are recovering, as I said, we are recovering the architecture and design with EPI, and we need now also to recover from technology fabrication in Europe.
If I may chime in, this is Fabrizio. EPI is tasked to develop a complete ecosystem end-to-end, which means that the working system for users. The initiative in the link is basically focused to the microprocessor.
Okay, thanks, Fabrizio. What's meant by automotive eHPC? eHPC, it's for embedded HPC. It's for automotive means that nowadays for automotive we need more and more computing performances, and the chips that are able to the data cruncher, let's say chips, are very more and more, let's say, closer to HPC like of processing. So that's why we need for automotive the performance of what is inside HPC chips, but with some additional requirements that are not easy to to follow, like real-time requirements. So that's yeah, that's a difficult job to design an automotive eHPC chip derived from HPC1. But we need this processing power for HPC. Obviously, for automotive, we'll have only one chip, while for HPC, we will have thousands and tens of thousands of these processors for the complete system. So in HPC, we have to handle the parallelism, while it is not the case in automotive, because we only use one processor. So how does the consortium work? Is there a page providing info on how to join the initiative, member, tiers, funding, terms, and so on? Yes, so the consortium is assigned the FPA, Framework Partnership Agreement, with the European Union. There is a website to describe the initiatives, who are a member of these initiatives. Perhaps, or if Mario is connected, can explain how to join the initiative. If somebody wants to, but we have some partners joining the initiative. For that, don't, let's say, be in touch with Mario from University of Zagreb. He can explain how to get information and how to join the initiative. And are there similar initiatives to develop European design and manufacture GPUs, mass memory modules, RAM modules, VR devices, and smartphone modems, etc.? I don't know, perhaps, but I don't know. I'm not informed about this kind of initiative. So if somebody from the EPI audience is able to answer, don't hesitate.
I see no raised hands here, so continue, please.
Yeah. May I ask, are there any plans for creating software abstraction on our heterogeneous architecture? So I'm not the software guy, but we have a complete work package dedicated to heterogeneous, let's say, software definition and development. So I would prefer somebody from the software to answer, but this is something that we are working on, which is not so easy. So we have this, even if we obviously we are mainly targeting the semiconductor devices or processors. There is a real lots of work as well on these software layers. So for on-chip and off-chip integration of custom accelerator for other buses in logic, is it necessary to license IP blocks from US companies that might be subjects of embargo? So the goal is to avoid, obviously, the goal is the following: at the accelerator side, is to be able to avoid any licensing from US company, so that the people working on the accelerator who would like to be compatible with a common platform, to be able to do it without any, let's say, link or dependencies with US companies. So this is our goal. Not easy to fulfill, but this is the goal. does the package shows automatically the deployment course, or is it a common problem? I don't really understand the questions. We have a common problem, which is the link between accelerators and the host, the processor. Obviously, the package will embed both. In case we embed an accelerator in a chiplet way inside the package. So we cannot have a common package, since the accelerator could have different pinouts. But all what is common, I mean hardware, interfaces, software, we are developing it.
There's just only one more question in the chat room, so I will read it, and then we have to really move on, because the next presentation is on. How important is RISC-V for EPI?
RISC-V is important for the accelerator side, so we believe that RISC-V is the right course to leverage accelerators, and accelerators is the only way to specialize some part of the application, so that we are able to sustain an exascale level of performance. So RISC-V is let's say a big part of the API developments, especially for accelerators.
I think we covered all. I'm not sure if there was one more in the chat, and I think that's the last one. Will this European processor be freely licensed and open sourced from the software and hardware perspectives?
Which part of EPI fully licensed?
It does not specify. The question says, will this European processor? So I'm guessing. So
the European processor is industrialized by Cypher, so for as a component. But this is not, let's say, an open hardware provided to the community. It was this kind of questions, Katarina?
Yes, yes. Thank you all for questions, and thank you, Denis, for your introduction. We have already breached our time by 7 minutes, so I would like to invite Professor Saponara from the University of Pisa to now start his presentation. After which there's a break of 10 minutes, so we can steal a little bit time there. Sergio, would you please?
Okay, can you hear me?
Yes, we can hear you.
Thanks to Denis for his introduction, and thanks to University of Zagreb, so Katarina and Mario, for the wonderful work in coordinating the dissemination of this kind of project. I will start sharing my screen. Okay, I will try to be as fast as possible. So I'm Sergio Saponara. I'm full professor of electronics at the University of Pisa in Italy, and particularly in the European Processor Initiative. I'm the work package leader in the stream 2 for the general purpose processor for the hardware security implementation. So the security part of the GPP. So in this brief outline, I will share the main idea that are at the base of the European Processor Initiative, and particularly to the general purpose processor, and how this idea found implementation in an hardware security module called the SMS, so Security Module Subsystem, that is one of the tiles of this heterogeneous processor. And we will see the feature that it has, since it's a programmable tile, thanks to a RISC-V programmable core, plus hardware acceleration, called cryptotile of several services, symmetric cryptography, public key cryptography, secure hashing, digital signature and verification, on-chip random number generator, that have been specifically designed. And also I will show what is foreseen in the evolution of the roadmap for hardware security in the European Processor Initiative. Obviously, I'm presenting this, but let me acknowledgement that obviously these are results of collaborations, since security is an important topic of, we were speaking of sovereignty, so of the European Processor Initiative, so it's treated in many parts. So there is in the Stream 1 work package 2, that is a work package led by Denis Dutoit. There are system level specification of the security. Then in Stream 2 for the processor, beside the hardware security module that I will discuss in this presentation, there are also aspects related to the software part and to the integration in the general purpose processor of software toolchain. Then, as we said, the goal is not only addressing needs, scientific needs of the HPC world, but also the needs of high-performance computing is increasing also in other markets, for example, automotive. And indeed, there is a continuous collaboration with automotive Stream 4, where are involved companies like Infineon, BMW, Electrobit, in order to ensure that what we are designing can fulfill also the requirements of the automotive world, where autonomous driving will need what was explained before is called embedded high performance computing. And then in our stream, we are in WP that I'm leading, we are taking all the aspects related to the hardware implementation, but also all the, let me say, low-level software services related to the boot, to the OS microkernel, and so on. This is why, obviously, is a result of a discussion with other partners. Let me acknowledge that we have continuous calls with Patricia Mo from Prove and Run, Christian Zotier and Ying Ji from Cyperl. Also, for example, the specification where also the documents were reviewed by Daniel Schreckling from BMW. And obviously, this all I'm presenting cannot be possible without the hands-on work of a wonderful group of engineers at the University of Pisa, Luca Baldanzi, Luca Crocetti, Francesco Falaschi, Stefano Di Matteo, Pietro Nanni-Pieri, that are a part of the strategic vision, then making possible the implementation of this work. So, as already said, the security is a key part of the European Processor Initiative, since maybe one can argue that an heterogeneous architecture based on ARM plus some coprocessor is something that you can find also in other part of the marketing literature, but security, like for example power management that you will see later addressed by colleagues of University of Bologna, are some key differentiator and are customizing the processor for markets where obviously technology non-dependency is important, like automotive, where European industry is a leading worldwide, avionic, aerospace, and then the spin-off in markets like robotics and Industry 4.0, and as we said, also high-performance edge and cloud. So obviously what I'm discussing is foreseen as a programmable and scalable IP, so can be configured in different way to address different needs. So in the as showed by Denis before, EPI is growing up several technology. We are focusing here on the general purpose multi-core architecture. Then an industrialized version of this will be bringed on the market by the company Cyperl. So the core is an heterogeneous architecture where you have ARM core, but is not only an array of ARM SV core. So it's not, there are also new products emerging like the Fujitsu, for example, ARM SV based. REA can be more than this, since potentially in the European Processor Initiative there will be some coprocessor specific for some application, like MPPA from Calray, or the European accelerator that is led by BSC, but is mixing contribution from several partners like Zurich, Fraunhofer, CA, Semidynamics. There can be also the possibility is developed also an embedded FPGA technology, and one of the tile is dedicated to security services, and as I said, is foreseen as a reconfigurable and programmable one in order to adapt the needs of the security to the different markets. To this aim, so the core obviously is of such a complex system is a network on chip. One of the tile is the SMS, security module subsystem. Then, as I said, together with also the power management PMS that will be discussed by the group of University of Bologna, is something that is making this ARM-based solution different from any other, and is characterizing the fact that for the critical parts, security and power management, all the design is based in Europe, and is increasing the needs of the capability of European design. Going more in detail, obviously, I need to keep at least I can the general, since some details obviously are also linked to IP rights of partners and cannot be disclosed. So I will try to disclose what I can. So the idea is that the general purpose processor will support the concept of trusted zone. And so at the end, you will have multiple domains where for each domain, there will be a dedicated secure part, is a programmable part. So there is no risk of obsolescence, since obviously there will be some dedicated accelerators to some services, but at the end you will keep back compatibility also with old security services, and this upgrade to new one, since there is a programmable part with dedicated memory in a secured zone. As we say, this part is ensuring for each trusted zone, so it's separating the concept of trusted zone. So let me say already the European Processor Initiative, the GPP, is ready to support advanced concept like hypervisor, virtual machine coexisting or different domains, since you can have a zone with a different level of trustability. And obviously there is a secure part that is supervising all, using also the technology dedicated solution, like for example one-time programmable of unclonable function, or refuse to have a technology integrated approach. And also the DMA has a security dedicated. So this part that are integrated in this subsystem will ensure, let me say, an hardware-based root of trust that adds on the security level that you can have already, let me say, for the fact that you have ARM. So all we are discussing are solutions that are characterized, you can find only in the European Processor Initiative, and you will not find in a generic ARM-based processor. This is why I say that HiPEAC is more than just an heterogeneous integrator of ARM cores and other. Giving to, let me say, zooming, so entering in each of these is a repetition of a structure that will look like this. So at the end, you will have, this is a secure MCU providing security services to the zone. There is a programmable part. This is needed both to ensure compatibility to, for example, hold services that maybe does not deserve to have an hardware accelerator. Let me see, for example, for security hash accelerator, no, the one used now are 2 and maybe in the future 3. As SHA1 is no more used, but again, you need maybe there are some standards that are still using the one version that is old, you can support on software, and this is kind of an example. Or also in the future, if you want to combine new services, this will give programmability. There was a careful selection of the core was selected, the RISC-V, in order to give, let me say, sort of diversity again in terms of security with respect of the fact that is ARM-controlled one. And so, let me say, this was also clever, since then you know the story of NVIDIA acquired ARM. For the security, for the SMS, this will not change nothing. In terms of security for the RISC-V in AP1 is giving programmability is an Ariane IP that is one designed by the group of University of Bologna and Zurich, while in the future evolution of API is also foreseen to modify the RISC part, maybe to embed also some security services also in the accelerator and even in the RISC-V, and this will be done in collaboration also with BSG and Semidynamics. So you have this programmable part, some memories kept in a secure zone, the accelerator that is you can see as an array of axis slaves with and these are we will see the main characteristic of these are based for different types of symmetric cryptography, asymmetric public key cryptography, hashing. Then there is also a random number generator. Plus, specific for the security element, you can have this, let me say, you can resynthesize 7 nanometer, 6 nanometer, 5 nanometer FPGA. This is scalable RIP. Instead, these are technology dependent, like and are one-time programmable memory or refuse needed for, let me say, secure boot and also anti-tampering and this kind of stuff. Indeed, has a general specification that are implemented through this architecture. Is first of all is the results of the specification were done after an analysis of the threats, vulnerability, and errors, taking care not only the high-performance computing scientific scenario, but also the automotive one. Indeed, is already in automotive. There is the Evita full. Evita is a full de facto standard for security. Evita full is the maximum version, and already the GPP is compliant with the Evita full, and this thanks also to interaction with Infineon and BMW. Then obviously there are all some specific solutions, since each engine internally we will see as dedicated register, dedicated parts for configuration and control, for a secure management installation of the keys, for secure configuration of the IP, for a continuous control and cryptographic operation. There are also features for secure diagnostic, anti-tampering, and obviously support of all the security operation needed in the most diffused standard like TLS, SHA, MAX, HiPEAC, Wave, and so on. So at the end, the GPP is ready not only for the high performance computing scientific part or automotive, but also to be used and to compete in the market of secure general purpose processor. And as I said, spec were revised both by automotive partner and by general purpose partner. Just to give an overview of the performance that you can achieve, for example, for the symmetric cryptography is supported IS modes. IS is there is an IS core, but then you have multiple modes of operation. Is supported up to 9 modes of operation that are de facto all the one used, and also in terms of extension of the key, you know that there is IS in order to be ready for post-quantum cryptography. The classical key of 128 bits used can be not sufficient in a post-quantum domain, so we already support an extension up to 256. Also, for example, for the hashing, so we support the 2 and 3 versions that are the newest one, and also we extended with respect to classical solution that today are 256-bit. We doubled this size in order to be ready for post-quantum cryptography. Instead, for public key cryptography, we support, so in software, RSA, while in hardware, the elliptic curve cryptography, and all the families, so the interaction to the programmable part, all the family of different techniques, like elliptic curve digital signal algorithm, elliptic curve integrated encryption scheme, elliptic curve Diffie-Hellman, elliptic curve maintenance Q-Vanstone for authentication key agreement. So all the elliptic curve based approaches for public key cryptography. This is supported in hardware. For this part, no, if we look to post-quantum cryptography, for the IS, for the SHA, will be enough extending the bits. For the public key cryptography, can be needed to instead to go to post-quantum scheme like Lattice 1, as are will be standardized in the next years by NIST and by other entities, and is already part of, we will see, of the roadmap of EPI. So anyway, the goal is having IP that are ensure the compatibility for the next 10 years, but also we are considering the compatibility also when quantum computing will arrive. Then, as I said before, some random number generator or solution that are technology dependent, there is also, we proposed a true random number generator where is exploiting a flow more related to standard cell, so is needed obviously a careful place and route, but is a TRNG based on Fibonacci and Galois digital ring oscillator, plus a cryptographically secure plus pseudo-random number generator that can have the feed from this TRNG, or for example a full custom TRNG, and then creates high throughput seeds, random seeds. This is needed, these high throughput random seeds, in order to have a very fast change of the key. All this stuff obviously have been implemented. I will go now quickly in order to answer then the question in a dedicated and scalable IP. So the crypto tile that you look here is mounted in an AXI. For the moment it's AXI 4, but we will support also in the future evolution the key. So the version 5 is obviously not only cryptographic engine making the mathematics that were background IP of University of Pisa, but then have been extended to support also specific register, finite state machine to manage this kind of feature. And beside the integration in the target REA technology, so in nanoscale technology, there will be the creation for the SMS also an FPGA-based prototyping board, where there will be integrated in Ariane CPU that, as I said, for the moment is taken as it is, but can be in the future modified. Obviously, there will be some interfaces for debugging for on-chip ROM and RAM, ADMA that for the moment will be taken, can be an available IP for Cypel, maybe we'll use an ARM DMA, but can be also modified, plus all the security IP development. You have already heard the numbers when integrated in FPGA part of SSU 106. In order to have exploitation, also try to integrate more things, try to make more modification. And since the goal is not the FPGA version, we will port this on a VCU 128 that is has more FPGA resources, so will allow also to be an open platform for testing all the idea on also the new components of the AP1 and maybe 2 cryptography. Then very rapidly, so for each engine, obviously, there is a dedicated design. Some works have been already published. So for example, this is in the last number of microprocessor and microsystem. You can find this value. Other is are under review. The message that I want to pass is that these engines are also flexible. So for example, obviously, we support 2 and 3. In the full version, you can support SHA 2 and 3 with the maximum size. Obviously, you pay a little bit complexity than the basic solution, but you have a full support in hardware. And the complexity, if we see of this, is low when compared. So we are less than 100 milliwatt to support these services compared now to the 100 watt of the overall. So let me say the cost of, obviously this is only one tile of, but the cost is really value, the fact that you have this kind of services. And in terms of speed, obviously we are targeting already throughput that maybe are quite high, since for each configuration we will see that minimum we are in the order of 10 gigabit per second to hundreds of gigabit per second. This will depend on the configuration then we want to achieve. This is for SHA. For elliptic curve cryptography, for example, again, synthesis is 7 nanometer ASIC technology. Obviously here again is a very configurable, so will depends what you support. If we support all, so the 256 and 521 version, the gate counts is in the order of 500,000 of gate with supported frequency of in the order of little bit less than 2 gigahertz, but also the power consumption cost is not a limit. This is the cryptographically secure pseudorandom number generator. Also, this has been already published, and this can take seeds from the external seeds or the internal TRNG. So you have also a very good flexibility, and also in this case, all these IP have been tested with respect to the testing suites of standardization like brands, like for example NIST in US, and are passing this. And also the complexity, again, you have seed generation in the order of several tens of gigabit per second. In such case, for example, the maximum clock frequency 5 gigahertz, then obviously the architect can design to have all this IP at the same frequency or have separated clock domains when integrating. And also the complexity, I think it's limited. This is the IS. Also there we support multiple, as I said, cheaper modes. Since each cheaper mode is specific for a service of confidentiality or integrity of authenticity. So since a general passport processor, you want to support different markets, you have different IP, you do not pay if you support 9 modes 9 times the complexity, since obviously there is an optimization. And these are the results. Obviously, there is a trade-off in the configuration between throughput and logic. So for the implementation, maybe area, we selected these to keep low the complexity that already ensure tens of gigabit, but maybe, and this can be one of the results of EP2, you can design, for example, a very high throughput dedicated almost 400 gigabit per second engine. Obviously, in such case, increasing the number of stages is increasing the complexity. Indeed, to give a look to which is the foreseen evolution, maybe in the roadmap. So having high throughput, so above 300 gigabits IS60 SAP, this is a dedicated encryption for memory and fast I/O. Support, giving full support to post-quantum cryptography, that for the IS and SHA is already there. Maybe for the public key cryptography, NIST is under standardization for sure lattice schemes, so maybe having support of post-quantum cryptography standards for key generation encapsulation. this. And then this is an idea that we discussed with the University of Bologna, maybe try giving these two important tiles of EPI that are the PMS and the SMS, maybe try to merge and maybe give some services together to exploit also this capability. Plus, obviously, when the chip will turn back, there will be a lot of work on then assessing and certifying the performance. And in case we are already integrating services to have side resistant to side channel attack, and we will measure, we will assess this. So let me say, more than enhancing is more certifying, the security level that we have. So as a conclusion, the hardware security module, this SMS in EPI, provide a programmable, so there is a programmable part, root of trust with acceleration support for all the security services that you may think of, so encryption, hashing, signature, key generation, encapsulation, is compliant, is foreseen to be compliant with several markets, so not only scientific application of FPGA, but for example, very challenging market like automotive. Already there is a roadmap to support post-quantum cryptography, so post-quantum crypto is not a problem for EPI. And this is what's important. Obviously, there will be some dedicated services for the software, but is already foreseen to be compliant, let me say, with any operating system, and is already ready to support concepts like hypervisor and virtual machine.
Sergio, can I please just interrupt you really quickly? Okay. We have already started eating away at our break, and we have a couple of questions. Would you be okay?
So I've ended. Sorry for...
No, you didn't go over your time. We just are 5 minutes late as it is, and I would really like to address the questions because...
Okay, very rapidly, I will address the question that maybe I will go...
Do you see the questions in the question and
answer?
Yes,
I see.
The first one is from Thomas at 8:45.
Okay. So very rapidly, there are similar needs. Okay, RAM module. Okay, that's the package. Okay.
The question that started when you started
talking. Okay, so I will try to resume. I see some question about the use of the RISC-V. Okay, as I said, for the moment here, the RISC-V is used as a programmable part to ensure compatibility, backward compatibility. For example, SH1 is not supported, but this can be run via software on an Ariane 64. So for the moment, the RISC-V is not a modified RISC, is taken as is the Ariane to give programmability. In EPI2, for example, is foreseen a work dedicated on giving security on RISC-V. So here, the use of RISC-V is we can substitute the RISC-V, for example, with the Cortex-M, having a not so complex processor like another ARM, having a diversity, since if we are controlling, giving the security an ARM-based, it's better not to have ARM. In the IP, in order to give a certain programmability, was selected the RISC-V. But here, for the moment, the RISC-V is the Ariane IP, giving a sort of computation programmability. The security services are provided by the round. In the evolution, is foreseen also to go deeply and have a secure RISC part that maybe in that case cannot need all the accelerator services that are provided here. So give a sort of scalability.
Okay, the next one is, does the general purpose CPUs contain metric counters that can be analyzed by the secure tile to identify statistical deviations that might hint at...
Yes, for this part we have, as I said, in the description of the feature, there are several resources that are implementing techniques to take care of side channel attack. And indeed, one of the goals of the EP2 will be in the bring up measure this, since obviously we are making a design, we are synthesizing some feature when we speak of side channel attack. So power attack, electromagnetic attack are really then related to the hardware implementation. Indeed, one of the goals will be measuring the level of resistance, but already this kind of countermeasure are already foreseen in the design on that part that in the presentation was called the wrapper or control register, status register, and this kind of stuff. So it's already foreseen.
And two more from Tony, and then I really would like us to have that break so that people can, you know.
Okay, since there is a question, but I think it's more to Denise. I really don't understand Denise's answer, so maybe
Yes.
this is
okay. Denise will cover this one. But how does the performance of
this processor compare to high-end Intel i9 or AMD Ryzen processor? Let me say, we will. This will be the goal of the. In terms of security, I think we will support all the feature that a modern unit will support. One of the goal of the bring up will be having the chip and and then making the measurements, and we will see that for security, I think the service provided will have nothing to let me say less than competitor. For other performance in terms of AI accelerator, linear algebra computing, then I leave to my colleague to answer. But for the security, I think it's also support. What does the role of PUF, which kind of PUF the system use and why? For the technology part, these are part of the CyPEAC that is directly taking care of parts that are taken from the technology. So for this, I cannot share any information since obviously is let me say we are entering the secrets of the company, so I cannot. I'm not allowed to answer.
Can I stop you now, because we have now answered to all the attendees. We will try to collect all your questions and try to answer them also in a written format if this is going to be possible. So we will later share it on our social media. But it's 4:10 already, which means that we have eaten into our break entirely. And I know Sergio has some university duties he needs to leave. So I am suggesting we take our break now and come back to the presentation that will be held by Fabrizio Magugliani, if I'm not mistaken. Yeah, update of the PCIe boards as development testbed for EPI. So it's 4:10 now. Please, let's reconvene in 4:20 for the remainder of our presentations.
So just thanks to all the attendees for their question. Obviously, if there are other questions, you have my contacts, you can contact me, and if I can answer, I will answer. Otherwise, I will, as I said, some parts are not shareable, and maybe I will forward to the guy from CyPEAC. Okay, bye-bye.
Thank you, Sergio, and we are now on a break until 4:20, as I said.
Can I take, this is Fabrizio, can I take the screen?
Sure, I wanted to share our countdown timer, but if you need your screen, sure. Take the screen. I am writing in the chat so that you guys know we are back at 4:20 from our break. So this is your not on screen break.
Oh. Does it work, Katarina?
Yes, I can see your screen.
Okay.
Okay, so we come back at 4:20, and I will now pause recording so that we don't have 10 minutes of pause in our.
Okay.
It's a great thing that I mentioned now the recording, because I just resumed recording. Fabrizio, you need to unmute before you start. So we will now continue with the part related to the PCIe update.
Thanks a lot, Katarina, and thanks a lot to the team. My name is Fabrizio Magugliani. I am with E4 Computer Engineering, and I will present the EPI PCIe daughter card, which is positioned inside EPI SGA1 as the software development vehicle. The rationale for the approach of using a PCIe card is having something cheap, relatively cheap, easy to design, easy to install on a wide range of platforms, having a PCI slot, and honestly, in these days, no one doesn't have a PCI slot, and flexible in terms of configuration, affordable in the meaning that a lot of users outside the EPI consortium may install it, and having the opportunity to receive feedback from the real world. Therefore, the idea was to having the PCIe as a sort of precursor to the HPC blade, which is under the development of Atos, and the PCI daughter card may be easily installed in several different markets, providing feedback and usage in different areas. Therefore, the objective is enriching the wealth of data, getting to the development team to improve the design of the second generation of the processor. As Denis has been showing, this is the roadmap, and the PCI daughter card basically fits there. At the end of this calendar year, we will have the PCIe boards, and they will be available for the general market with, as I mentioned before, with a full set of software, development software for using them in a real-world environment. As a preliminary layout, this is the preliminary design of the PCIe GPP daughter card. As you may see, there is the processor in the middle of the board. There are all the power supplies needed to keep the board running, and not showing in this slide, there are all the ancillary equipment, fan and whatever need to be put on the board, on the system, to make the board work. The board will also be measured in terms of stability and in terms of reliability. And as I mentioned before, all this data will improve the design of the second generation. This is the PCIe GPP daughter board. The PCIe test chip daughter board is based on a FPGA by a known provider, and the test chip, will fit in one of the FMC Plus slot as a daughter board. This technological solution will increase the number of options we have to possibly expand the number of options we have, and test different configuration within the same base, where the same base means the same FPGA board. As I mentioned before, this may fit in a standard PCI slot of the server. Of course, it requires a special setup, but that's nothing that will imply a major rework of the architecture. I'm coming to the conclusion, and my talk is brief because the complexity of the processor has been already covered by Denis, and the other feature will be covered by the other speakers. As a conclusion, the PCIe daughter board is the ideal software development kit to enable a wide number of users to have access to the system, to make tests and provide feedback information to support the second generation of the system. I ask you to stay tuned, and all the timeline of when the boards will be available will be posted in the website. With this being very quick and having gained some time for the overall presentation, I give back to Katarina the control of the screen. I cannot see if there are any questions.
Thank you, Fabrizio. I don't see any questions in the Q&A for you, and also not in the chat. I see somebody, I don't see the name, who mentioned that the sessions, the organizer announced that the sessions will be recorded. Yes, the sessions are being recorded automatically, but this is why only our faces and our voices are shown, not chat history or not anything that might reveal your data. We know we're very sensitive about our data in Europe, as we should be. So the next presentation is by our colleagues from CEA. As I see no questions for Fabrizio, we can continue if you guys are ready. Lilia, for the next one.
Yes, hi.
Perfect.
Did you hear me correctly?
Yes, we can hear you and see you. You just need to share.
Okay, I'm going to share my screen.
Yes, I will now stop Fabrizio's screen, and you can now have full control of webinar.
Okay. Is it all right?
Yes,
I don't see your screen yet.
I see you, Lilia.
And my screen?
No,
Yeah,
not
not
yet.
yet.
Can you please check? Ah, yes, now we can see your screen, but we can't hear you. You're muted now.
This is the typical demo effect. Everything has been working fine during the tests.
Do you hear me now?
We can hear you.
Okay, great. Do you get my slides?
No.
Okay, I reshare.
Okay, please do. Lilia?
Yes, is it
okay.
okay now? Okay,
Perfect.
great.
Okay, we can see your slides and hear you.
And see me?
And see you, everything.
Well,
okay.
Sorry for these issues. Thank you, Katarina, for your patience and the invitation to this tutorial. I'm Lilia Zaourar, research engineer at CEA List and work package lead for simulation activities in EPI project. With my colleague Tanguy Sassolas, we will present you today SESAM VPSim, fast and highly configurable simulation framework for the EPI processor. This tool has been developed since many years in our laboratory, and I want to thank here all the people that contribute to this work, from PhD students to permanent colleagues, in particular the one that worked the last months within EPI project. As you all may know, virtual prototyping is nowadays needed to design complex system on chip. In fact, it allows fast design exploration and improve design quality. It brings a virtual hardware platform to software designer to start developed software environment. And thus it allows the integration and pre-phase testing and reduce time to market as represented here in my schemes. The agenda of my presentation is the following. First, I'm going to present you the context of using SESAM VPSim in European Processor Initiative and give you VPSim background overview. Then we will present in details recent evolutions of VPSim with the 0.3.0 release, with the cache models, the NOC, and some numerical results. We will then detail co-simulation parts for verification of safety critical application. And finally, some conclusion and perspectives. Last but not least, we will have a video demonstration of the tool. So please stay awake until the end. VPSim is a virtual prototyping framework, a part of SESAM environment developed in our laboratory. VPSim aims to help early software development, performance profiling and debug, design space exploration through efficient simulation, and hardware validation, as well as cyber physical system prototyping. VPSim can easily interface with other simulations tools, thanks to systemc, TLM, and FMI standard. VPSim provides a Python script to describe the platform that we want to simulate with large and flexible IP portfolio, and perform a rapid simulation able to run full software stacks. Of course, simulation tools are a must-have to have in a project like EPI. The figure here depicts the 3 different simulators tools that we used in the project. Each of them is in a different level, from architectural exploration and analysis to software development. We have MUSA, which is a system-level simulator developed by Barcelona Supercomputing Center, GEM5, a precise simulator from ARM and a well-known simulator, and VPSim, which is used by various project partners because it covers different levels and needs. VPSim could be seen as a Lego platform where it's possible to develop IP models in VPSim or plug external models developed by other partners, as represented here, and simulate the whole platform in a unique framework. Thus, the aim of VPSim is to provide a virtual environment for software development and hardware-software co-design. It helps software teams get started with early testing and preparation of software environment and test suites. It supports all levels from BIOS to OpenNPI. And from the hardware part, it is useful for API processor specifications by early identification of performance issues. We can see here in the figure the common platform part that can easily interface with external and industrial simulators. We have here an overview of the processor architectures. It has been presented by Denis previously, which is a heterogeneous platform with many core processors, accelerators, etc. It requires latest processor features to enable software environment like ARM scalable vector extensions and performance monitoring units. And of course, we need for speed, for full server OS and compilation environment, as well as accuracy, with a special focus on memory subsystem with NOC to identify bottleneck. To address these challenges, we make some specific development in VPSim with a special focus on cache model coherency and NOC. We also make the choice to structure the simulator around the KEMU, as represented in the figure here. We developed some statistical model to provide temporal performances, and it is possible to deactivate this part in order to gain performance. For example, if we only need software development, as it will be presented in details later. We also collaborate with partners to integrate some specific needs and features like I/O and NVMe with Forth or FME part with UNIPI. And I will also present this part in details here. I leave now the floor to Tanguy for this second part.
Thank you, Lilia. So now that we've seen the call for simulation in the EPI project, I will briefly focus on the key features from a user standpoint in VPSim before focusing on specific development performed within the EPI project. So VPSim is meant to really rapidly set up a platform. To do that, we provide VPSim as a simple compiled simulator, which encompasses all the available model in the system. So there's all sort of models within VPSim that are pre-compiled. And of course, we want to keep high configurability to set up platform for the user. So all these can be set up using a higher level of abstraction with the Python configuration front end. We'll see in details how it works. And it is also extendable because all the data here exchange can be also set up using a graphical user interface. And among the models that are made available, several of them are meant for co-simulation with external tools. We'll come back a bit on that later on. Once the user has set up a platform using the high-level Python interface, VPSim will simulate the behavior of the platform by leveraging the systemc simulator and produce statistics, fine-grained statistics, debugging information. So you can use GDB to develop softwares on top of VPSim for more efficient software development ahead of time, ahead of the availability of the circuit. And we can also provide some efficient statistics and monitoring features to the user. So having seen that, we're going to focus on how this does work to set up the platform in VPSim. So VPSim, upon startup, is able to describe a list of supported components and their supported attributes so that the user is aware of what can be changed and set up in the platform. So this is done in a standard XSD file that describes available parameters, and that is imported by the Python design-specific language to describe more accurately the platform. So finally, setting up a platform can be very easy. So here we've got a simple platform which creates a system bus with a given latency. We can create a bit of memory, like here we're instantiating 1 GB of memory, and we're connecting this memory to the system bus. We also can generate an intercontroller, a UART, and then instantiate several processors. So for instance, here we are instantiating Cortex A57 processors. So once the hardware platform is set up, we can also give some parameters that set up the software part. So here we are loading a device tree blob in the RAM and also an image file for the OS to run correctly. So all this description in Python generate an XML file that specifies the platform that is to be used by VPSim, and VPSim will interpret it to instantiate during simulation the given platform. So this would in turn generate XML statistics that can be retrieved within the Python environment for the user to process and perform required analysis for instance, design space exploration. So having illustrated how the VPSim platform works in general, now let's focus on available IPs in the system. So we've got mainly 3 types of IPs. We've got built-in systemc TLM components that were designed internally. So for instance, you can already use SRAM, DDR controllers, caches model, there was an interconnect, simple peripherals, and of course, interrupt controllers. And so this is one big part of the models available that are pure systemc TLM ones. But we also leverage the rich model library available in QEMU, which is not actually a simulator, but more of an emulator. And we'll see later on how we integrate QEMU within VPSim to provide a full system simulation. And finally, we've got some specific third-party components that are used, well, specific components that are used to co-simulate with third-party subsystems. So for instance, in the EPI project, we've used that extensively to support ARM fast model co-simulation. So in terms of QEMU integration, we support various aspects of QEMU within VPSim. So we support the CPU models that are integrated into systemc threads and for which we can monitor the memory accesses and then forward them to the full memory hierarchy for a full system simulation. But we also support peripheral simulation that can be instantiated as other threads as slave on the bus. And one of the advantages of using VPSim is that all the complexity brought by QEMU models can be abstracted, because VPSim will provide a simple interface with standardized attributes to be changed for a given IP. So for instance, here we're instantiating a simple UART that is provided by QEMU model, and we connect it to the bus. So this is mainly straightforward. Speaking about performance, so QEMU is known to be really fast in terms of emulation, thanks to dynamic binary translation. And we've managed to keep it that way whenever DMI, full DMI is allowed, so that memory accesses just bypass the memory hierarchy. Otherwise, the other accesses to part of the system that we want to simulate are unhandled by systemc simulation, and which has, of course, a performance impact on the overall system. So speaking about speed, so it is well known that it's impossible to have both fast simulation and accurate simulation because the rapidity comes at the expense of loss of accuracy, loss of detail, and loss of accuracy. So usually fast models, they lack the precision needed for efficient design space exploration, while accurate models, they lack the speed to really encompass full system simulation, especially for large-scale systems such as the EPI platform. So what we've set up here is we try to achieve a good performance accuracy trade-off by enabling the user with dynamic accuracy management, which can be applied both on the hardware part and on the software part, which means that you're able to set up which level accuracy you need for each piece of executing software, and also which level of accuracy you require for a given hardware IP in the memory hierarchy. So this can be changed easily by the user to enable VPSim to be used in several usage mode in the EPI project. So from lower level characterization with timing, more accurate timing and the statistics accuracy for design space exploration, but also faster simulation for software development. So now that we've talked about a bit of performance, let's see about interfaces with external tools. So VPSim supports full FMI and RTL co-simulation. FMI is a standard for system simulation, and we've implemented in VPSim as well. VPSim supports FMI as a slave, so it's a functional markup unit, which allows better coupling with other external tools, not limiting to only slave FMUs. And so this can be used, for instance, to co-simulate with sensors, sensor simulator or simulator dedicated to other domain than the pure system virtual prototyping. We've used it, for instance, for simulating autonomous vehicle by getting the data coming from LiDAR, radar, and cameras and processing the data into a virtual prototyping of the ECU. And we also support co-simulation with RTL, which is more standard with systemc. This is very efficient when you use it for validation of design under test, where you want to really have the accuracy brought by the RTL for the peripheral under test, but you want to keep the remainder of the simulation fast using more abstract models to reduce design cycles. And one last type of external simulator integration, we support full external simulator integration as a peripheral on any interconnect. So this is a VPSim specific interface. So here you can see in the Python interface that you would create an external simulator whose address whose address space would be starting at 0x8 0000, and you would then call an external library that would implement the standardized C API that we set up and provide also an interrupt number to this model. So here, the interface is pretty simple. I mean, there's mainly one main thread, which is called Run Simulator, which is launched upon simulation startup, and in which the external simulator can implement any thread he needs to actually perform the simulation. Then data exchange take place using simple write and reads to the memory space specified when instantiating the simulator. And of course, then there needs to be some way to call VPSim for interrupts. So we provide a callback mechanism for interrupts and also for timing synchronization, so that both simulators can execute in parallel. So having described some generic features of VPSim, we'll now focus more on the model that were designed for the EPI needs, and in particular on the memory hierarchy, so cache modeling and NOC modeling. So initially, VPSim did support complex cache system modeling, but it didn't support currents protocol. The currents was, I would say, free thanks to DMI for the memory access itself. And so we've added simulation of state-of-the-art currents protocol so that to enable evaluation of the cost of this currents on the EPI platform. So this is not the actual current protocol of the EPI, but it is similar in terms of performance, and then it will allow VPSim to simulate large-scale system and see the impact in terms of currents messages. So all this model was validated using assertions, so a thorough validation with more than 160 assertions. And it is also to be noted that though the statistics are accurate on this currents protocol modeling, the timing impact of the currents is an overestimation due to the fact that this is the worst case time model. So penalties are fully taken into the system, and this does not account for reordering, prefetching, out of order execution. So this is something we want to really work more in the future to really better fit timing simulation to the EPI needs. So in terms of instantiation of such a memory hierarchy, so nothing changes in terms of cache description. One mainly needs to activate a flag to true to enable the coherence, and then to modify the hierarchy. Here you can change, for instance, the number of cores per cluster, which would change the size of a request node, and set up the interconnect. So the current protocol interconnect automatically between all the caches in the cluster. So in terms of statistics provided to the user, you would get all the statistics relative to coherence-related messages. So this would provide a detailed view on coherence impact on the simulation. And we would also provide some more general purpose counters based on this more detailed statistics, such as hits and miss in the memory hierarchy. So this can be used to evaluate a given topology in terms of messages and efficiency of the future platform. In terms of NOC modeling, then here we can see we had a simple NOC model that would account for topological aspect of the network on chip. So it would take into account the number of hops required to get from a request node to the target node. It would also take into account the time to transmit the data and the physical delay brought by the routers, as well as the length of the packets. But this simple model didn't take into account contentions, actually. So we improved it to take into account this in an abstract manner, because we don't want to lose too much in terms of performance by taking into account contention. So all this work was published at date 2021 and will be presented in the next 2 weeks. So when setting up this new NOC model, again, one needs to trigger a flag to enable the simulation of the contention model. And then one important parameter to look at is the contention interval. So this is a defined amount of time during which the usage of the network will be somehow simulated to account for occupancy of the resources of the network on chip and account for contention within this time slot. Then you would have, so this would increase the simulation. The higher the number, the longer the simulation, and the smaller the number, the less accurate it can be. In terms of parameters of the NOC, you would have all the usual parameters that you need for a network, so the buffer size, in terms of number of fleets, the latency of the routers and of the link, as well as the number of virtual channel in the platform. So in terms of statistics, the user can be provided with simple statistics such as the number of packets transmitted by the NOC or the total distance crossed in hops by the packets. And of course, the most common data of the average network latency, which gives a good idea of how occupied the network is actually. So looking at performance, so as I said, this model is meant to keep a good performance while providing appropriate accuracy to the needs of the EPR project. We compared this model with more detailed and more accurate Garnet model. What we can see is that we reach an acceleration of up to x14 compared to Garnet simulation. And we can also see that the higher the number of packets transiting within the NOC, or the higher the NOC size, the higher the speed up is. So this is really a model that is well suited for large-scale simulation and large-scale systems such as the European processor. So though really fast, this model still has an impact on the overall VPSim simulation, which is in the order of a division by 2 of the simulation speed with respect to alleviating, well, ignoring totally the contentions. So based on this new contention model, we are able to really see the impact on the network latency of the contention due to the increase in the usage of the network. So here we can see the curves are actually growing with the number of fleets transiting per cycle. And so you can start making design space exploration on the size of the mesh and on the impact of the total latency on this network. Here again, by changing the buffer size, you can see that increasing the buffer size does limit the average network latency and can bring performance improvement. So this kind of results can be really helpful in designing large-scale multiprocessor systems. But we need to be confident in the accuracy of the model. This is why we characterize the models against Garnet again. So here we can see that the curves from Garnet and the curves from this abstract model within VPSim do fit very well. This is for 2 different topologies, so a 4x4 mesh or an 8x8 mesh, both using XY routing and 2 virtual channels. So this is very good results in terms of accuracy, and the same applies when we change the VC size the curves still do match between Garnet and the proposed NOC model. So we've got a good accuracy, which makes us able to really simulate large system with confidence. So now that we've illustrated some new models meant for added accuracy in the modeling, I'll let Lilia continue by focusing more on the speed aspect of VPSim.
Thank you, Tanguy. Now I will present you some numerical results to highlight the good trade-off that we have with VPSim between speed and accuracy we can notice that within EPI project, we leverage several simulators to best fit all design needs, from architecture exploration to software development. We consider that having consistent results between the three simulators, MUSA, GEM5, and VPSim, is crucial to make a reliable design decision. Thus, a co-validation campaign of simulators was conducted. We used different benchmarks. We present here two of them: FMI to stress CPU bound and STREAM to stress memory bound. We use a single ARM core with 3 cache levels. The diagram here represents the amount of simulated instruction per second for each simulator. Since GEM5 is a precise simulator, it is slower than the other ones, of course. We also are 5 times faster than MUSA here. In order to help design space exploration, we also provide various hardware performance counters. The table here describes the different set of counters we have. We have cache counters, instruction counters, operation counters, and simulated time counters. Here is an example of instruction counters with FMI benchmark and memory access counters with the same benchmark. We notice that we have 0.3% error compared to GEM5 and 3.6% error for memory access counters, which are quite good results regarding the architectural details that are simulated here. Now I will give you a quick overview of co-simulation of FMI co-simulation for safety critical application. Thanks to easily interfacing SESAM with the external simulator, we can proceed to co-simulation for a critical application. We have here an example for automatic transmission controller with a transmission control. In the left side of the figure, we have a vehicle model and engine transmission, and in the right side, we have we can execute the control application, and we get the information that take into account the timing, thanks to virtual prototyping. This was a joint work with University of Pisa that we published a few months ago. We have here the impact of simulated CPU speed with 2 different scenarios. In the best one, the automatic transmission controller execution duration is shorter than the FMI co-simulation step, and output values are updated at every step. Consistent result with more abstract modeling of application execution. And in the worst case, the automatic transmission controller execution duration is longer than the FMI co-simulation step. Output values are updated in later simulation steps. We tested with added delay loops of the application code. Here are some curves for co-simulation results, resulting execution profile, and the difference with abstract control code modeling when facing too long execution duration of the control code. To conclude, we've seen that virtual prototypes are needed to abstract simulation models that enable software development in the absence or with the limited access to the hardware, which is the case at the beginning of EPI project. It helped to reduce the lag between hardware delivery and software availability, and thus improve time to market. VPSim tool provides a good compromise between accuracy and execution time. In fact, it achieves high simulated speed to enable the simulation of large HPC processors from design space exploration to software development. The tool, due to the abstraction of most hardware modeled, simulation accuracy is kept high, with error limited to 3.6%, as we show in previous figures on performance counters. Several interfaces are provided to enable efficient co-simulation at several levels of abstraction, ranging from system simulation with the FMI standard to external TLM peripherals and RTL simulation. By leveraging QEMU library as well as some in-house models in VPSim provides a rich model library to build a new platform in a friendly Python script interface. Of course, there are still some possible improvement in VPSim tool. For example, we would like to further improve the timing accuracy of VPSim, which is important to enable architecture decision through efficient automated design test exploration. We would like also to leverage VPSim co-simulation capabilities to couple it with other partner simulator tools and provide a system simulation, for example, with Synopsys Virtualizer. We would like also to define some novel parallel methods to accelerate the simulation of memory hierarchies for ever larger HPC models and keep enriching the model library. I put here some references if you want to go deeper in some of the subjects that I presented here. We also have some patterns for some technical parts of the simulator tool. And thank you for your attention, and we are going to present you a demo. Just let's Tanguy again.
It's not working with the link. I think it's due to the pointer. I'm just going to remove the pointer and then, okay, there we go. Thank you. So I'm going to present briefly in a few minutes example platform built thanks to VPSim for the need of the EPI project. So here we're going to be setting up a very simple use case to illustrate how it can be done in a very fast manner. So here we've got a simple RISC-V processor connected to a bus and some memory around on the RAM and a UART, and executing simple software which is bare metal. And here on the right side, I hope you see better than I do actually. We can set up the whole platform. So first we can set up the application that is going to be executed on the platform. And then we can configure the model that is described in the picture. So we're going to have the processor. We're going to find the RAM that we're going to be instantiating and all the connections to the bus, which should be around here. And then we'll be launching the simulation that is described in this Python script. And we'll connect it. We'll connect to the platform. So here the application started, and we're going to connect to the UART to see the application actually displaying a Hello World, Hello EPI project. And finally, at the end of execution, we retrieve all the statistics from the simulation that are directly dumped by the system. So now we can move on to a more complex platform, which is more akin to the actual EPI platform. Here, so we've got a 4x4 mesh with 2 cores per request node. And so this is a tiny bit more complex platform, and we provide for the need of the EPI a more simple description that constrain a bit available parameters of the platform to simplify the platform generation. So here you can see the parameters of the whole cache hierarchy and of the actual network and chip configuration. So based on this script, we're going to start the execution of this platform and booting Linux OS. So here we can see the Linux boot in real time. So you can see how fast the platform actually does run for software validation or simulation. Once we will have booted, we will use a small utility software called SESAM that is made available within the Linux kernel that allows to activate the monitoring of performance statistics in the system. So we're going to be executing a tiny script that's going to launch 2 benchmarks and retrieve statistics for this given benchmark in some text file. And then we can use SESAM quit to actually quit the simulation. So this can be helpful to run also simulation, VPSim simulation in batch to retrieve lots of data for efficient design space exploration. And here we also see upon termination that VPSim provides all the statistics of the system. So here on a per CPU basis. So based on that, we can really leverage VPSim for exploration and co-design. So here we can see on the left a figure where you have the impact of the memory size of the cache hierarchy on the performance of several benchmarks. And we can also study, for instance, on the right, performance impact brought by the network on chip with the latency achieved for a given benchmark for all the CPUs in the system. So this is just simple example of what can be achieved with VPSim. Okay, so thank you. Thank you all for your attention. I'm going to switch off the sharing. I don't know how you can switch off while you're still seeing the demonstration.
It's okay.
It's okay. Yeah.
I will relinquish you of the power to share your screen when it's time for the second presentation. But in the meantime, we have some questions. Tony here asked 2 questions. I'm not sure about the first one, if you'll be able to cover. If not, then I will defer it to later when we'll all hear. So I will read the first and the second one, and then you'll tell me if you can cover this. General question about EPI. Are you using formal methods in what different areas of the development? I'm not a technical person, but as far as I know, in verification, we are using.
So the short answer is no, we're not using formal method, even though we've been using assertions for to ensure correct implementation of the currency protocol. But there's no actually formal verification here. So it's more based on experimental validation with respect to more accurate models to provide good accuracy performance trade-off.
Okay, the next question, also again by Tony, which parts of the EPI team will be using VPSim and in which contexts? With what other simulation tools will be used and in what context of the development?
Okay, so I don't really, if you want to answer, there are several. Well, there's several.
Yeah, there are several partners that use the VPSim, as I show in my slide in the beginning of my presentation. We have, for example, Fraunhofer. We have Forth, UNIPI. Don't know if you want me to go deeper in which part they use the simulator, but it's.
So it's related to co-design activity for some parts. So for the partners that Lilia stated, and we also are going to work in conjunction with Infineon to validate full system simulation using the GPP and automotive domain accelerator.
We also have Atos, yes, that use the simulator for HBM and DDR memory simulation parts.
So it's really a full toolbox. I mean, that thanks to the interoperability, we'll be able to co-simulate also with industrial flows, like stated by Lilia with Synopsys suites.
Okay, thank you. And I see another question. There was another question, but it's no longer there. I just see one more now by Thomas, who asked, what's underneath the simulation in terms of hardware?
On the given use so it's a standard Intel server processor that we are using here in terms of host processor for the simulation. Yeah. So there's no specific hack here.
We use our personal laptop, for example, to run
Thomas,
the simulation.
sorry, yeah. Thomas asked a single CPU.
So in this actual simulation, there is 2 CPUs, I think, one for the CPU part and another one for the memory hierarchy modeling. But we've also worked on accelerating through multiprocessor acceleration, the system simulation, but this has not been set up in the EPI project. So far, the answer is 2 processor. Yes.
Okay, I don't see any more. Oh, I do see, sorry. For a single CPU, says Thomas. And then Tony asks, is VPSim software or it is a service? Does it cost anything?
Well, so we are a tier 1 RTO organization. So the software is shared with the EPI project partner for free,
of course.
But for other use cases, I mean, you should rather contact us directly so that we can discuss whether we could share some licenses with you and on which basis.
Yeah, don't hesitate to send us a direct email and we can discuss more details together.
Yes.
Okay, guys, thank you very much for your presentation. I don't see any more questions in the... I have really scrolled now. There are no more questions in the chat nor in the question and answer section. We had a break planned here, even though you finished a little bit early, which is kind of impressive. That I remember how many slides you had. Can I just have a quick check here if Andrea and Giovanni are here? Can you hear us, guys?
Yes, I'm here.
We are here.
So what do you say we reconvene in 15 minutes or so? So maybe 5:25 to start your presentation.
Okay.
Yes, 5:25. Is that okay?
For me, yes.
Giovanni?
Yes, perfect.
Okay, I see here 47 attendees. I hope everybody's okay with a break like this. So I will now type in the chat that we are back at 5:25 with your presentation, which is the final one for today. And then after, I hope I will get all of my panelists back for maybe another quick session of questions and answers. Okay, so see you in 10 minutes or so. Thank you. Again, I now remember that we need to resume recording. We are now recording, and welcome to the last session, or I mean last presentation from this tutorial. Once we are finished, I hope to have the entire crew here back for maybe a couple of additional questions and to close the day. Andrea, the floor is yours.
Okay, let me share the screen. You should see now the screen.
Yes, we see.
Okay. Okay, so the presentation of today is shared with Giovanni Bambini. We are both from University of Bologna. So I'm Andrea Bartolini. I'm assistant professor at the department, University of Bologna. And what I'm going to present you today is the work we have done in the context of EPI on developing the power controller unit subsystem for the API processor and the challenges and that we are facing in co-design it. I would like, before starting, to thank Katarina and Mario for organizing dissemination activity of API. We really appreciate all your work. And so I'm trying to do all my best to give a good presentation here. So the the work of the outline of the presentation. So first I will discuss the problem of power management in HPC system. We heard from the Denis speaking, from the Denis presentation, the fact that energy efficiency is a constraint for today and already for yesterday and today supercomputing systems, and it is even more for the future generation one, as we are since a decade in after the NER scaling ends, and each generation brings increased power densities, and it is critical to manage the power consumption inside the processor, not only for the efficiency to power the entire system, but also to be capable of providing the current to the inside the chip, and also to be capable of being thermal sustainable. Then I will present the power controller subsystem designed in EPI. We will present the fact that it's an open source design and also the firmware, and which means open source means it is based on the pulp-based architecture, which makes it suitable to be open source. We will describe the software architecture and the hardware in the loop methodology, design methodology that we are using for testing it and developing it. So what is a power controller in the context of HPC system? So power controller is a unit, is an hardware unit that sits inside the processor and have to interact with many actors. These actors are actors which are hardware actors, which are outside the processor but in the motherboard, and other actors are software and platform management actors. So the power controller talks outside on the motherboard side with, let me use the laser pointer, talks with off-chip components, and also on chip it talks with the processor elements. Indeed, it controls the power consumption of these processing elements that enables decides the frequency at which they have to run, and it also reads sensors, which are utilization, silicon quality sensors, and also thermal sensors. It also has to interact with the software stack, so with operating system application and system management and resource management. It is an HPC system, so you don't have only one node, but you have thousands of millions of them, and you want to and you schedule application. User does not see directly the hardware, but see a job scheduler which executes its own job scripts inside a portion of the nodes which are available on the system. And so power controller interacts with the operating system by providing two kinds of services. One is the telemetry service, so is the how much power is my software consuming, or which one is the performance at which the power controller was allowing the course of the processor to execute. And then it also interacts with the power governors. If we speak about a Linux operating system, we have power governors which implement to the user of the system the frequency abstraction, so on which the user can request a given frequency for a given processor. And so underneath the governors, who takes the real decision on which frequency at which each given core is running is the power controller unit. And then also there is an increasing requirement in the HPC context also to enable a interaction of the power management policies which are executed at the level of the application or at the runtime to be capable of interact with the power controller bypassing the standard interfaces which are in the operating system. So these can be so to implement hints and the prescription from the application to the hardware of the system. Then we have at the highest level of abstraction, we have the job scheduler, which and the system administrator, which to which the power controller has to implement services which are power capping services, so control the maximum power consumption of the node or for the socket of the system, and so achieve the maximum performance under a power budget or achieve the maximum energy efficiency at a given performance target, or maximize the throughput under a boundary in power and temperature. This is the so-called in-band path, because all the information travels through the operating system, which runs on the core, on the processor itself, to the application and to the job schedulers, which also talks to the processor through the operating system, which runs on that processors. We have instead also the out-of-band path instead, which is the additional service that the power controller needs to handle, which is the communication to the external management connector interface, which is usually called board management, is implemented through the board management controller, so the BMC, which realize the out-of-band communication. So through that path, there are standards and interfaces which allow to retrieve from the system administrator the quality of the node, so its own temperature, power consumption, different telemetry, but also infer from out-of-band the control actions, such as the maximum power consumption of the node, or also monitoring the RAS, so the reliability, accessibility, and serviceability of the system. So also error reporting and conditions. So all these services has to be implemented and realized by the power controller unit in the context of an HPC system. And of course, as you can see, designing it poses challenges in terms of the emulating all these, evaluating and emulating all the interfaces with that components. These components are really heterogeneous because you have really dedicated hardware controllers, you have processors, you have sensors, but you have also operating system application and also system components. And this, so it's challenging. We'll see in the second half of the presentation how this is done. Then at a given point, I will switch and give the word to Giovanni Bambini that will give more detail on the firmware, on the power controller itself. So as I just said, the power controller is a power controller subsystem. It's really a key ingredient inside the server platform, which is designed to prevent thermal hazard, ensure a TDP power budget consumption under any condition and any workload, and also increase energy efficiency. And it requires a dedicated microcontroller inside the system to handle it. And it has to do several tasks, the one which I described before, and so it also requires to run a firmware that is capable of realizing advanced controller policies, which consist of computationally intensive tasks to execute a firmware based on real-time operating system to allow a more sophisticated software, and also so it requires more power microcontrollers. In addition to that, there is also the trend of, in general, to try to embed in this component also advanced functionalities such as AI or machine learning capabilities, which can help in the task which has to do. So if we look at the state of the art of power controllers in the between different vendors, this is a slide that I take from the Power Stack Initiative, HPC Power Stack Initiative from the meeting of 2019. Here, what is listed are the different vendors and the different capabilities in terms of monitoring, control, and interfaces for the power management. And what we can see here, a little bit highlighted, are the time scales at which and the granularity of the monitoring of the power consumption and of the utilization of the different cores, sockets, memory, and accelerators, nodes. And the time scale we can see is around of a millisecond and hundreds of microseconds in terms of the monitoring, self-monitoring of the power consumption, and the time scale instead for the control for the power management is in the range still of millisecond and hundreds of microseconds. So if you take Intel, for instance, the internal logic changes frequency allows the software to change frequency at the speed of 500 microseconds, and the power capping logic internally works at a frequency at the time scale of milliseconds. Then we have, at the level of interfaces, we have several interfaces which change a little bit between the different vendors. This is not really completely standardized, so each own vendor has its own interface for interacting with the low-level power management features. And we can see that among the many, there are specific architecture-specific registers, libraries such as performance monitoring libraries, which wraps these registers. There are also some action in creating open source firmware, which are already taken, which are almost a standard today for the BMC firmware, such as the OpenBMC, and also some vendor proposes some dedicated memory map interfaces for sharing the informations with low latency between the user space and the hardware without having to change the operating system. So the target in the AP design, we target to support a power controller subsystem which supports fine-grained power monitoring and control, and also which is capable to implement hardware advanced power controller algorithms. The design within API for the power management subsystem relies on a dedicated subsystem, hardware subsystem, and controllers in a dedicated network for interacting with the sensors and actuators which are available in the system. And also, a decision that we take is to implement it based on RISC-V instruction set. And we used for that purposes the PULP platform as a base for implementing the hardware power management subsystem. And on top of that, we extended it for being a power controller, and also we developed all the power management firmware which interacts with the different actors that we depicted before. And it is an open source design, so it will be openly released, and we will see this a little bit later. The benefit of just a little bit of work on the PULP project. So the PULP project is an idea of designing a complete vertical stack, hardware and software stack for open source microcontroller and more powerful microcontrollers, so parallel microcontrollers. So it composes of many IPs. These IPs are several cores and also interfaces and interconnect, which allow to create an architecture which is a parallel microcontroller system. So it exploits both a instruction set extension for DSP, which becomes really handy when we're doing DSP and signal processing operation, which are needed in the power controllers, and also machine learning and deep learning workload, and also parallel architecture, so exploit also parallelism for having additional performance gain at the scale of a microcontroller, which really well fits the needs of the power management subsystem. It is a mature. That's the first benefit of PULP. So it's been silicon proofed and used by many industrial partners. The license allows to use in industrial project without no restriction. It is more powerful than competitors' state-of-the-art system on chip on the same scale. So it is smaller when compared to an ARM M4 and M7, and it achieves higher performance when dealing with complex and application based on AI and edge. So it can achieve on an AI application up to the 36x faster than compared to a M4, and 8 times faster when compared to an M7 system. So it's more performing. And that's why we use it for the design of the power management subsystem. I will now leave the word to Giovanni Bambini, which will continue on the presentation.
Hello, thanks, Andrea. When we decided to the design for the PCS, we opted for open source hardware and software. And so we went for the Pulp project for the hardware, which, as Andrea said, is powerful and also energy efficient, and also quite innovative, and can support a more advanced algorithm and also machine learning quite easily. Instead, for the firmware, we decided to go with an RTS, so a real-time operating system, and we chose FreeRTOS because it's open source and well-established product. Using RTS help us in the firmware development because it's more flexible and powerful than bare metal for a cost of some slight overheads. Regarding the control algorithm, we went for a block cascade design. We have two main blocks, the power dispatching layer, which is the block that decide the powers to give to each component and core, that feeds this power to the next block, which is the thermal control block, which decrease the operating point in order to enforce the thermal limit for each component based on the silicon technology. The power dispatching layer has an algorithm that gives power based on the thermal room available for each component in order to prioritize the hottest components and the hottest cores that are supposed to be computing the more demanding task. Instead, the colder cores and components generally are executing some memory-bound computation. And then we can see later the results that we achieved. And then instead, the thermal control block contains one PI for each component. And the inputs of the API are the thermal limit of the silicon technology minus some margin and the temperature sensor of the component, so we can achieve a good and smooth control. Thanks to the advancedness of Pulp hardware, we can also add some other blocks like some model adaptation block to feed better parameters to the power dispatching layer and the thermal control to improve performances, and also some machine learning or IA to predict the workload that is going to be done to improve also the power utilization and power budget. The firmware structure is divided in region. There is the PCS region, which is the open source one. It contains the FreeRTOS region that has several tasks that has several features inside them, mainly regarding the controls, but also communication and management. And there is also an hardware abstraction layer to translate these inputs and requests from the FreeRTOS task to the PCS hardware. And then there is the outer region that is the PMS, which is the vendor implementation of the PCS, because it has to translate for the communication, for some events management, and for some other features that are present in the vendor system that can be called inside some FreeRTOS tasks that are designed for that. The IOs of the PMS is this one. We take some inputs from the sensor and the cores, like the temperature of the components or the some performance counters from the cores or the power consumption from the VRs. but also we take inputs from DOS and the BMC, like some commands, some target frequency, some target operating points, some configuration, and also a new thing that we introduced that is the binding matrix that can be fed to the PCS and PMS that can tell us if there are a group of core that are executing parallel workload. In this way, we can optimize to share, to balance the workload, so the cores will end at the same time improving the performances and also the energy efficiency of the overall system. We also, as input, some commands and data from the SMS, which is the security management subsystem that feed us the initial configuration, and also some boundaries and constraints that we need to enforce in the outputs. As outputs, we give operating point to the core and computational unit, such as voltage, frequency, throttling, plus some additional feature depending on each vendor. And also we give to the DS and the BMC the telemetry, errors, and infos of the runtime, and also some performance counters and parameters. The scheduling we are adopting now in FreeRTOS is the rate monotonic scheduling. So we have several periodic tasks that are paired with harmonic relation period to each other. The rate monotonic scheduling is supposed to be optimal. And also the scheduling is preemptive in FreeRTOS. Here we can see an example of the control tasks that are executing and preempting each other. Regarding the tests, we designed an hardware in the loop emulation. So we wanted to have a complete and good simulation of the chip and also the controller, so we could do some hardware software co-design and co-simulation. That was really important to us. And so we choose as platform the Xilinx ZCU102 that has four ARM A53 cores and 2 ARM R5 microcontrollers, and also an FPGA that we programmed with the PCS and PMS hardware. Is to measure the overheads of the RTOS and the performance of the control mainly. We decided to simulate the API SIP or the SIP in general in this way, which is the core 0, and we put a discrete time state space simulation for the thermal and the temperature of each core. We have 2 states for each core, and we are simulating up to 36 right now. And also we have an algebraic computation for the power simulation. In another of the 4 ARM A53 cores, we also simulate the operating system that gives through the XCI the target frequency and commands, and gather information regarding the data and infos and errors of the PCS. We also put a third code in one core for the sort of governor model that is connected to the Ethernet port, and it gathers all the infos for further and later analysis, and also can take instant commands to be sent to the PCS for be applying instantly. In the next future, we are also adding the BMC as an agent to the Xilinx platform that will be connected through E2C connection to the FPGA, and we will implement it with OpenBMC on a Raspberry Pi or literally BMC. Also, another project is to implement on the Xilinx board the SCMI ARM protocol for the communication between the OS and the PCS. These slides will show the results. The overheads that we measured for regarding FreeRTOS and the RTOS is about 6% in the nominal case and 9.5 in the worst case. That are totally acceptable, seeing all the benefits that the RTOS is giving. If we also consider DLOX as part of the overheads, the number increase a lot, and this seems that we need to improve the hardware implementation of RTOS lock, but they are still good numbers. Regarding the power dispatching algorithm, that is the one that is dependent on the temperature room of the core. If compared to a naive equal power dispatcher, we can see an improvement of the 13.7% for the power budget utilization, and also the more demanding cores, the other ones run in average 700 megahertz faster, with a boost of up to 1.8 gigahertz compared to the naive power dispatcher algorithm. On the right graph, we can see the control performance if we consider some decided inputs to test all the features of the control. We can see the step at as an initial command, and we can appreciate a really low overshoot of 41 milliseconds and just maximum 1 degree higher over the lower thermal limit. We can see that the power budget is fully utilized and respected, and also that the frequency is kept at maximum possible. And so thanks for your attention. I will give back the words to Andrea.
So for concluding, what we presented today is the overall structure of the power management subsystem that we are designing for the EPI project, and also the hardware platform on which is created, and its own interfaces and the firmware which runs on it. Of course, it's a teamwork. Here is the name of all the contributing to this activity, and also it's also the link to the PAL platform project on which the open source part is going to be released. We are also, the second part was the challenge of doing the design of of this controller, which is really a cyber physical system, because you have to interact with many systems, which requires a co-design hardware in the loop methodology in order to do it. Thanks for your attention. I don't know if there are questions.
Thank you, Andrea. Thank you, Giovanni. There are 3, as I can see for now. So the first one is by Tony, who asked, what is the telemetry for physically connected debugger devices for the OS to display temperatures, etc.?
No. So the answer is that the telemetry is for user and system administrator. So you have to imagine that in HPC system, you have that the core is going to run for, you have 1,000 of nodes, which have eventually 2 sockets, so which have many cores, and each user wants to optimize its own code. And so the user wants to know why my code was running at that given performance and the reasons of that. It wants to know also the energy consumption of their code. And lastly, the system administrator wants to know why and how the system is the given node was giving a given performance. So telemetry is in the sense is not a debug telemetry, so it's not an externally attached debugger, but it's telemetry which has to go to the application and to the system administrator. Okay, Antonio's question is, thanks for your presentation. Do you use IPs from Xilinx? It will be possible to use Intel FPGAs, Altera in your methodology. Thanks, Antonio, for your question. So since the PULP is a completely open source project, so all the IPs that were used are developed, and so this can be synthesized on any architecture. on any FPGA architecture, and also the also silicon. Of course, there needs to be all the synthesis script for the FPGA and that part are gonna be released for the one that we use, which is Xilinx. Benefit of the ultra-scale architecture of Xilinx is that you have on the side already some ARM cores which you can use for running the models, but also for emulating the true core. And in case of an Intel FPGA, it would be the same. So you have on the other side Intel core, so there will be no problem for doing that.
Okay, thank you. And the last one I can see here by Farnam. How could you ensure that the temperature of each core is produced by that core since they're close to each other on the chip?
Okay.
I can answer. Okay. Do
Yes,
you wanna...
Giovanni, you can go.
Okay.
No, you can go.
Regarding the simulation, we have the state space that with the matrices that take into account this close vicinity and interaction between cores temperature. So in the simulation, we took that into account. Regarding the real system, we cannot be completely sure. We can only read the sensor temperature, but that's what we have a margin for. So we have a margin in the controller. So I mean, we can still avoid reaching the thermal backdown or the thermal limit of the core.
Yes, I agree with what Giovanni said, and also since we measure the temperature of sensors which are physically located in the nearby of a core, we measure the heat produced in that region, and the algorithm is aware of the fact that there are cores in proximity.
Thank you. And I see another one. I just saw it. Just give me a second. How are power side channel attacks taken into account regarding telemetry? And then there's a link for an example, platypusattack.com. I don't know if you can click it in the Q&A.
I can click on the link, but I can answer to this question. It's a really interesting question. So, indeed, there are a short answer and a long answer. I will try to be short. So first part is that the PMS interacts with the SMS. So the security subsystem module interacts with the power management subsystem module. And that's ensure that the security is taken in account also in the power management subsystem. Indeed, the power management subsystem is some sort of slave of the SMS. And on the power side channel attack, it's really depends on the level of granularity which you give to the user, and this depends on policies that the system administrator of the supercomputer will implement and will decide. So that is taken account at that level. Moreover, there is an ongoing discussion and ideas for, but this is more on the research side. We have several ideas together with Sergio on how we can improve this resiliency by doing something smarter inside the power controller and security subsystem module. But this is more work to be done. So the side channel is somehow in an HPC system is prevented by the fact that the machine are in a room which are for which the access is controlled, so no one can enter and connect devices to that to do it. And from the software side, it's really related to the frequency at which you provide out the information. Moreover, second part, sorry for stealing the time, Katarina, to answer it. The user mode of an HPC supercomputing machine is that a user own a portion of the machine for a given amount of time. So you don't have other users' code running on that system. So that part is also increases a little bit, decreases the risk of side channel attacks.
Okay. I see no more questions with regards to this last session. So we're at the end of our presentation sessions. I thank again all of you, to my presenters and panelists, and of course to the faithful audience, which has endured some screen time again. Avengers, assemble. Are you here, all of you? Yes. I just wanted to give this last opportunity. I know it's 6 o'clock, but we have time until 6:30. Of course, we don't need to make for all this time, but if there are people who still have some questions from previous sessions or something that they mentioned that was not related only to the people presenting at the time, now would be the good time to ask them. For example, I do recall, I think it was Tony who asked, yes, I find it here, a general question about EPI. Sergio, I don't know if you can hear me. And
yes, and I can hear you.
The two of you were also before this question, so I don't know if you can maybe cover this for Tony. General question about EPI. Are you using formal methods in what different areas of development? It was directed, I think, at Lilia when she was presenting, but of course, it does relate to other areas of development for EPI. So Sergio and maybe Denis, if possible.
I want to say that thanks for the question. Indeed, one of the is a part of a collaboration that University of Pisa using the tools proposed by SEA, and indeed this colleague of mine, Cinzia Bernardeschi, is working with a group of Lilia, indeed to exploit how the methodology based on VPSim and SESAM can be also used in connection, thanks to a functional mockup interface with other tool, like for example, into GPS is another tool to make formal verification of the hardware software. And indeed, there is also a common paper between University of Pisa and SEA involving Lilia and other, is an example to application of this VPSim and SESAM and the formal methodology, so formal proven theorem tools to verify, for example, an automotive case in which software for transmission control is running on a tile of REA, and we will see in advance you can also give some constraint to be sure that some properties of safety are for sure ensured or not. So the question, then I leave the words to Lilia, is yes, also this kind of methodology is addressed, and what we have seen is that VPSim, SESAM, and all the tools proposed by SEA can be a good basis also in this kind of approach. Then I leave the word to Lilia.
Yeah, thank you, Sergio. Just to complete this part, as I said, really SESAM is like a Lego platform, so we can plug other partners' parts, and it is the case for the part with UNIPI. So they are developing from their side formal methods and all the stuff related to this part, and we can plug it. We can provide a wrapper to plug it in SESAM VPSim.
I don't know if Denis, you have something to add here, because Tony answered that his question was actually directed at everyone. So I remember that you were answering at the beginning some of Tony's questions with regards to licensing as well.
Okay, for the subject with Lilia and Sergio, I have nothing to add. Okay. For the licensing, I'm not the right guy to answer. The right guy to answer, or the right company to answer, is Cyper. But as a summary, Cyper is integrating the IPs in a chip, in a processor, and Cyper is licensing IP from the partners. And then Cyper sells the chip as any companies selling chip. So I don't know if it answered Tony's questions on licensing, but he has to ask. It's better to discuss with Cyper about this process, I think.
And there's another question by Thomas about control flow, but I can't seem to find it. So I just replied to Thomas in the questions. Okay, so
is related to security parts on the control flow and
Giovanni just sent me the question. Are you employing technologies like control flow integrity checking on the ARM side of the CPU, perhaps including CHERE for automotive, some cap extensions or Morpheus-like approach presented last year by Todd Austin for the RISC-V parts? Okay, now I remember the question. Sorry, Thomas, I couldn't find it.
Okay, so as I said here, the focus of what I presented is more on the SMS style than is taking control and is diverse with respect to the ARM. Then there are also other activities on the ARM core but there obviously there is also is part of let me say the relationship between Cyperl and ARM. So not all can be, let me say, disclosed, obviously, no, since particularly the security part is something that should be kept secure. So let me say the message is that the HiPEAC community is addressing security from different perspectives, no? Software, hardware interaction between the hardware security, the SMS and the PMS, and taking vulnerability attacks. Obviously, some parts, some solution can be disclosed, and you will find this presentation, some fact sheet, some publication. Other obviously are, we will kept, let me say, secure, due also to the fact that not all solution will be open and downloadable, but there are also interests. So, for example, one of the goal of EPI is really porting on the market this through Cyperl, and so then there is a question of IP right, and so then maybe it can be answered, but it's more a question to send to the some question to the general manager, and then see if they can be answered by, for example, Cyperl or not.
Okay, and I see one more that I remember you addressed while you were talking, but I see that Tony mentions it was actually addressed to also, I guess, everyone. From the security perspective, there were some comments from Sergio. How does the performance of these processors compare or will compare to high-end Intel i9 or AMD Ryzen processors?
So the target of API is to create a platform, a processor for high performance computing, which is compatible, which is, let's say, which has a performance which are the one needed by the exascale machine. So it has to be, it has to have performance which compares or outnumbers the competitors. So it's a processor which will compete in the market against the other processor.
Okay, anybody, anything to add here? No? I see no more questions in the chat unless I skipped something. Please tell me or wave at me if I did, but I think this is it because I scrolled until the very end here. I guess we've closed all the comments and questions from the question section. That would mean that we are finished for the day, and I would like to thank you all again, my panelists and speakers, for delivering the presentations and for participating, and of course to the attendees for listening in and for keeping this a very lively discussion, I must say. From the get-go, we had a lot of questions and a lot of chat comments. We will, of course, try to see how to organize some of these answers if these recordings will not be made available. But as far as I remember from also the comments that you guys wrote here and from the organizer emails, the recordings of the webinars and the workshops will be made available by HiPEAC and of course by EPI after the fact in our YouTube channel or on our social media. That is it for the day. Thank you very much, everybody, and enjoy the conference, the rest of the conference. Tomorrow we also have a booth at the Brazen virtual booth platform. And one of our colleagues here that presented today, Fabrizio Magugliani from E4, is also attending the industrial session tomorrow, where he will briefly discuss EPI as well. Thank you again, and have a nice rest of the day, and of course the conference. Goodbye.